Okay, we're going to solve some fun problems using the first and the second derivative. And the first problem will be find A, B, C, and D. These are constants. And I'm telling you that f of x is equal to, it's generally equation number cubic, a number times x cubed plus a number times x squared plus a number times x plus a number. And I tell you this function f of x, it has a minimum value at the origin at 0, 0. And it has a maximum value at 2, 2. Okay, we know it's a cubic, and we can actually graph this function. It has a min at 0, 0. And for argument's sake, let's say that's 2, 2. And if it has a min at 0, it has to be coming down like that. If it has a max at 2, it has to go up and come down at 2, at 2, 2. So there's the graph. There it is. And graph it, that was no big deal, but I need to find A, B, C, and D. There are 4 unknowns, so I have to come up with 4 equations. Well, I don't care if 0, 0 is a max or a min or whatever. It's a point on the graph. That means f of 0 must be 0. This is a point on the graph. That means f for the x value, 2, must equal the y value, 2. And it has a min value when x is 0. That means the first derivative at 0 must equal 0. Not that 0. The first, if you have a max or a min in any x value, the first derivative is 0. In fact, we have a max at when x is 2. So f prime of 2 must equal 0. Okay, and for the record, I'll put it down here. Let's write down what the derivative equals. F prime of x equals, well, you multiply the power by a, 3a, make the new power 1 less. Multiply 2 by b, make the new power 1 less, plus the derivative of a constant times x is a constant, plus the derivative of a constant is 0. I won't write that. Now, this equation says f for 0 is 0. Well, if you plug in 0 for x, you get b. Okay, you get the constant. Why? Because a times 0 cubed is 0, b times 0 squared is 0, c times 0 is 0. Add those zeros, get 0. And add d, get d. So on one hand, that's f for 0, but we know it's 0. Now, f for 2 equals 2. So I plug in 2. 2 cubed is 8. Times a, plus 2 squared is 4, times b, plus c times 2, or 2 times c, plus d. But we know d is 0. That should give us that 2. Now, when I plug 0 in to the first derivative, I'm going to get c, and it's 0. So I just learned c is 0. It's history. When I plug 2 in, I get 2 cubed is 4, times 3 is 12, times 8. Get 12a, plus 2 times 2 is 4, times b is 4b, plus c is 0. And this equals 0. So, over here I'll do the bookkeeping. A, B, C, and D. Right now we know C is 0, and we know D is 0. Okay. So I So we have 4 equations and 4 unknowns. We dealt with the first and the third. Okay, now the middle two, or the second and the fourth, that's going to solve A and B. For example, well, let's just take the second equation and simplify it. Let's divide everything by 2. Due to lack of space, I'm going to do that there. So I have 4A plus 2B is equal to 1. The last equation, I'm going to divide by 4. And it gives 3A plus B is equal to 0. Now, if I were a bit clever, I would have divided that last equation by 2. In fact, let us do that. If I divide that last equation by 2, I will get 6A plus 2B equals 0. Now the number in front of B's are the same. I'm just going to subtract the 2 equations. Negative 2A, this is 0, equal to 1. So then A is negative 1/2. So A is negative 1/2. And now we can find B. For example, from this equation, we know that 2B's is negative 6A, which means dividing by 2, in case you can't see it, that means B is equal to negative 3A. But we know what A is now. Negative 3 times 1/2 is positive 3/2. The A is negative 1/2, B is positive 3/2, C and D, 0. So in the very, very top, I'm going to write down what F of X is. And I'm going to copy pretty much from right here. Except C and D are 0. So it's AX cubed. Positive B is positive 3 over 2 x squared. This is the function that looks exactly like that graph. Okay, and it's x squared for those of you, for all of you who can't see. It's negative 1/2 x cubed plus 3/2 x squared. In fact, I'll let you see it. Hopefully we're having fun. And you definitely should be able to do these problems. They'll come up in your homework assignments. Hold on a minute. Alright, so we're going to start now with the second derivative. That's where all the fun problems seem to really be. You definitely should know how to graph this. Okay, so we want to sketch the following functions that have these properties. I'm telling you that f for 2 is equal to f for 4, and that equals 0. And I'm telling you that the derivative is less than 0 if x is less than 3. And the derivative is bigger than 0 if x is bigger than 3. And f double prime of x is negative if x is anything but 3. And given this graph or sketch f of x? Well, have to be very careful, nice and slow. Why don't we just tackle maybe one at a time? When x is 2 or 4, the y value is 0. 2, 4. The y value is 0. Okay. Now here is 3. 3 keeps coming up. 3 keeps coming up. Remember, no matter what I draw, I must cross here and I must cross there. It says that the derivative, I'm reading the second one, it says the derivative, the slopes are less than 0 if x is less than 3. That is, I have to draw negative slopes. Here's a negative slope. Here's a negative slope. Okay. The next line says, now the reason I didn't draw, the reason I dashed it is because I don't know if the concavity is down or the concavity is up. Like I said earlier, knowing the sign of the first derivative, negative in our case, does not tell us anything about concavity. It doesn't tell us anything about concavity. Okay. The next line says that the slopes are positive if x is more than 3. Okay? So of course I'm going to pick up from here, and I must cross this point. I must cross that point. Okay. Now, the graph tells me, the next one tells me, the concavity is negative. Negative concavity goes that way if x is not 3. Okay, so to the left is 3, it's negative. What this really means is f double prime of x is less than 0 if x is less than 3, and f double prime of x is less than 0 if x is more than 3. So less than 3. Oh, okay. So goes like that, concave down. More than 3, concave down. Here's my graph. The doxology, not the dashed line. You should definitely draw the dashed line when you're doing this. To dash it, because it's not part of the graph. Here it is. Here it is. There it is. Graph is done. And I lived up to everything. I lived up to everything. With maybe one minor exception. It looks like here that the slopes are 0, the tangent lines are 0 or negative. I really shouldn't be going down. Should be like that. Never equals 0. Same on the right-hand point. Can never really equal 0. Or get negative. Okay, there's your graph given those 4 pieces of information. This is important that you know how to do this. You know how to do these graphs and you're understanding this stuff. In my opinion, this is the test to see if you understand the last third section. Okay, let's do 1 or 2 more of these. And we don't want to have too much fun now. Okay. Suppose I tell you that f for 0 is equal to f for 2, and this equals 0. And I tell you that f prime of x is less than 0. X is less than 1. And I tell you that f prime at 1 is 0. And I tell you that f prime of x is greater than 0 if x is greater than 1. And then I make the statement that the second derivative is greater than 0. That means always. I generally like to draw or put the information down on things that are concrete. For example, f of 0 is 0. That's right there. F of 2 is 0. 1, 2 is 0. Well, I know that's concrete. That is, when x is 1, the derivative is also 1. The slope of 1 is like at a right angle. The thing is I don't know where f of 1 is yet. For example, if f of 1 was here, I would draw a graph that has that line would be the tangent line at 1. Either the line's up there, either the point's up there, or it's down here, or possibly it's right at 0. Those are the three cases. So we have to see which one it can be. So we dealt with this one. We have three possibilities for that one for now. Now, I know, so the thing, they keep talking about 1. Less than 1, more than 1. So let's divide this at 1. It says the slopes are always negative if x is less than 1. So that means it's coming down like this. Remember, I have to cross the origin. It's coming down like this. So that kind of tells. So maybe I should have drawn the second one first. Maybe they're giving it to us in the right order. So that means that these two cases, they weren't the ones. They could have. So I know that I must be, this must be the tangent line at that point when x is 1. Okay, I dealt with this one by drawing out line. Remember, this line is not part of the graph. You'll see what I mean in a moment if you don't get it yet. When x is bigger than 1, the slopes are positive. Okay, the slopes are positive. Oh, I have to cross that too. The slopes are positive. And I have to cross it too. There we go. We dealt with this one. The next one says the concavity is always positive. That is, the graph always goes like that. Okay. So, here's our case. I must cross here, I must cross there, and right there, that must be the tangent line. And it's concave up. Well, the graph is going to go just like that. Okay. From right here, we'll go like this, go like that. And there's the graph. There's the graph. The graph is in nice red color now. Concave up, I cross the two necessary points, and my tangent line at 1 is 1. There's your graph. Okay, you really should be able to do this. Just watch this video, for the next 3 hours. Just keep watching it and doing it. Try to do it yourself. Get stuck. Go back, see where you went wrong. Let's try one more. Okay, so we'll do one more and then a different type. Here we have that f of 0 is equal to f of 2, which is 0. We have f prime of x is greater than 0, provided x is less than 1. We have that f prime of 1 is 0, and that f prime of x is less than 0, if x is more than 1, and the second derivative of x is less than 0 always. So, when x is 0, y is 0. when x is 2, y is 0. That's what is meant by f for 0 equals f for 2, which equals 0. What this is shorthand for saying f for 0 is 0 and f for 2 equals 0. Don't say, well, f for 0 equals f for 2. What does that mean? It doesn't really mean anything. It just means that f for 0 and f for 2 equal the same number. What number? In this case, 0. Okay, so they keep talking about bigger than 1 and less than 1. So let's have this division line as 1. The slopes are positive for the function is increasing when x is less than 1. It's increasing. And I have to cross the origin, because they told me. It's increasing. And then at 1, the derivative, or the slope, is 0. So this must be the tangent line. And this next line says the slopes are less than 0 if x is more than 1. It's negative slopes. And I have to cross at 2. And I really should be dashing this line. Okay, and the concavity, the second derivative is always negative, which means concave down. It goes like this. Okay, and the high point, where the slope is 0, must be at 1. There's your graph. There's your graph. Okay. Now, I'm going to give you a function. Now, after to draw the first derivative. In fact, draw the second derivative as well. Given the function f of x, draw the first and the second derivative. Okay. Suppose you're given that function. The only thing is I didn't really mean to cross right at the origin. Let's ask you the origin. Alright. So in red, in black, that's f of x. In blue, we're going to draw the first derivative. Well, let's see what we know. We know at this value, the tangent line is 0. That is, the derivative is 0 there, as well as here. Okay. Now, let's just label this A and B. To the left of A, the slope is very positive, less positive, less positive, less positive. Okay, going to 0. Okay, so the slopes are coming down. The slopes are coming down. What happened? Okay. Now, the slope here is negative, more negative, more negative, more negative, and there's a point of inflection. It's now less negative, even more less negative, and eventually it's 0. So there's a special thing going on right here. From A to B, the slopes were always negative. The slopes were always negative. But they start getting more negative, and then they start getting less negative, and eventually 0. And to the right of B, positive, more positive, more positive, more positive. goes like that. So, since our original graph is a nice, smooth polynomial, there's not going to be anything funky about our graph. Our graph goes like this and like this. Our graph being the first derivative. Okay, let me get rid of all these dashed lines in case they're in the way. So now we have the blue graph. It's the first derivative. We want the second derivative. That is, we want the derivative of a function which happens to be called f prime of x. And I can say f prime of x is h of x. It is, I just want the derivative of h of x. I want the derivative of the function in blue. I couldn't care less what we call this function. I couldn't care less what we call it. I want the derivative of the blue function. Well, if the slope is 0 right here, that means I'm going to be 0 there. And to the left of that point, the slopes are very negative, and they go to 0. And to the right of this point, the slopes are very small, positive, but they get bigger. That is, I would say it goes like this. Yeah, of course it doesn't go like that. It goes the complete opposite of what I said. First, the slopes are very negative, and they go to 0. And then the slopes are very positive. It has to be 0 right here. Negative to 0, 0 to bigger. And there's your, I did promise to draw it in red, sorry. There is your second derivative. Right here. Boom. What's in red is the second derivative. If you want the third derivative, just look at the graph of the second derivative. Don't even worry that, oh my, it's a derivative. It doesn't matter if it's a derivative or not. It doesn't matter what we call a function. Draw the derivative of that function. Okay, let's try this one more time. Suppose you have a nice fourth degree equation. Suppose you have that. This we will call g of x. And if I call the derivative f prime of x, trust me, I meant g prime of x. Now, right there, and right here, and right there, those are, that's where the tangent lines is 0. So the derivative is going to be 0 here, and here, and here. Okay, it's going to be 0 here, and here, and there. Okay, now let's label these. A, B, and C. Now, to the left of A, the slopes are, all the way to the left of A, the slopes are very negative, and then eventually they're 0. So it's from very negative to 0. And then the slopes are positive, more positive, much more positive, the largest. Okay, but let me dash this, please. But after that, it's still positive, but they're getting less and less positive. That is, right here is a point of inflection. Right here. That's where the concavity changed. To the left of this mark, it looks like it's concave down. To the right, for a while, it's concave up. So the slopes are changing. They're still negative. What's going on here? What's going on here is I have to learn what a positive slope looks like and what a negative slope looks like. That's where I'm messing up. To the left of A, the slopes are very positive, with a less positive, and 0. So it's coming from positive down to 0. And then to the right of A, the slope is negative, more negative, the most negative, and they're still negative, but it's going to 0. Okay, they're still negative, that's why I'm below their x-axis, and it's still 0. Now what happens after B? Well, we should identify the point of inflection. After B, well, again, the slope is 0. Then they're positive and more positive and more positive and more positive. And then the most positive. Positive, positive, most positive. And then call this point D. To the right of D, they're all positive, but they're getting smaller. They're positive, I'm above the x-axis, but I'm getting closer and closer to 0. That's what that tells me. So let's try to erase this side work. Okay, what happens after C? Well, after C, the slope is negative and more negative and more negative. So it's going down like this. And what that tells me is, so I have a min here and a max here, and I must cross at A and B. That's what that tells me. I must cross at A, the first derivative. I must cross at B, and I max out at D, and we'll call that E. And max out, min out at E. So these dashed lines, very, very helpful. So I come from up here, up. Okay, so it goes like this, and like that. That is G prime of x. If you want the derivative of that, first I have to get a marker that I can see. Hopefully this mark is better. see it. Now, we want the derivative of that. Okay? And that gets drawn in red. So, has a horizontal tangent line at E, so I must cross there. It has another horizontal tangent line at D, so I must cross at 0. And let's see, to the left of E, the slopes are negative, but they're getting closer to 0. Between E and B, the slopes are positive, but after B to D, the slopes are still positive, but they're getting less and less positive until at D it's 0. To the right of D, the slopes are negative, and they get more and more negative, like this. And you draw a nice smooth curve that crosses these key points. It crosses at E and this point up here and this point here. And there's the flavor of the dashed line. That is, from this point, don't go like that. Unless the dashed line tells you to go like this. And to the right, go like that. But I didn't mean to cross at D. I blew that. I did mean for this point to be at D. So make believe it is. And what you see in red, G double prime X. Okay, you should be able to graph these type of functions. Good luck with this.